Okay, so last class we were thinking about formally working with probability spaces. Okay, so defining what a probability space is, and so in the process we mentioned the first two steps. Okay, so we said, okay, given a problem, what we want to do is we want to model the problem with the notion of a universe set. Okay, the universe is also sometimes called the sample space, and there's no unique way to write the sample space for a problem, but it should be general enough that you can think about the problem properly. And in addition, uh, you should populate it with outcomes that are kind of mutually exclusive. Okay. Uh, so anything that helps you think about the problem completely is and consisting of outcomes that are mutually exclusive is a good choice for the universe. And we did an example. Okay. In this example, uh, there are two parties in this game, right? And each person throws a die with six faces, right? But the catch is neither party can see the outcome of their throw. They can only see what happens with the other person's throw. Okay, so we had Adriana and Brandy, like they both have a six-sided die and they throw the die, but Adriana only sees Brandy's die while Brandy sees Adriana's die. Okay, and as a consequence, uh, so Adriana does not know what her throw uh, shows up, and neither does Brandy. Okay, and they're supposed to guess what is on their die. Okay, now the way we model it, uh, we wrote the universe. So the universe is the set of all possible outcomes here, and here we chose to populate the universe with a combination, a pair of numbers, and this pair of numbers is one for each die. Okay, so here 1 1 means that both Adriana and Brandy got one on their throw. 2 3 means Adriana got two and Brandy got three, and so on. Okay, and when we write things this way, there are 36 possible outcomes. Okay, and so this covers like all possibilities of these two die throws. Okay, does that make sense? Any questions? Okay, so now once you have the universe, you define the notion of an event. Okay, and an event is a subset of the universe, right? And we only give probabilities to events, right? So that means that whenever you're speaking of probability, we are speaking of probability of a set. Okay, that's part of the reason why we have been paying so much attention to sets in the first week, right? So everything you do is probability of a set. Okay, so for example, like if you want the event that Adriana throws one, what do? We are looking for the subset of the universe that matches this event. Okay, so one way to do it a little more formally than what we said last class is to say, okay, uh, take this statement, okay, and think of it as a logical evaluation. So Adrian, so and on each outcome, look at this outcome. Okay, so does on this outcome is the statement true or not? Okay, and if it is true, I put it into the event. Okay, so Adriana rolls one evaluates to true on all these six outcomes. It evaluates to false everywhere else. Okay, so only these six elements go into this set. Okay, so this statement is kind of the logical statement that is associated with this set. Okay, and that's how we populate events. Okay, so everyone okay with this? Okay, so so we had a bunch of examples, but let's do a new example here. Um, so let's do a little more complicated example. Um, Okay, so let's do this example. The sum of the two rolls is 7. Okay, so what does this event correspond to? What set does this event correspond to? Anyone? Very good. So you can start with 1 6 2 5 3 4 4 3 5 2 and 6 1. Okay, so these are how we write events. Okay, so even though we sometimes say a statement, okay, we say Adriana rolls 1 as an event. What we truly mean by that is that we look at the subset of the universe, okay, on which the statement evaluates to 1. Right, makes sense? Okay, right. So the natural next question is, how many different events could happen in this setup, right? And while we haven't yet done the computation, uh, in this sample space, there are 36 possible outcomes. The number of different events that can happen in this problem, in this setup, is 2 to the 36. Okay, now we may choose to describe the events any way we want. Okay, that's not, it's not the descriptions we are concerned about. Okay, we are thinking of two events to be distinct if they correspond to distinct subsets of the universe. Okay, and in that sense, the number of different possible events that can happen is 2 to the 36. How it is 2 to the 36, we'll come to it soon, and it's kind of an important story. Okay, but let's believe that number for now. Just believe me that so one of you told me, so I think, I don't know who answered, I think maybe Brandon, uh, but let's believe Brandon that it's 2 to the 36. Okay, so there are these many different possible events that could happen. Okay, now we had this so then we started looking at this, right? Like we said, okay, your job is to guess the number on your die. Okay, and you cannot, there are no tricks. You cannot communicate once you see the roll of the other person's dice. Okay, so the moment A sees B's die and B sees A's die, okay, they both have to uh, write down a number, and that number will be taken as the guess. And there's no collusion, nothing, right? So but there can be many strategies they can adopt. They can discuss a priori. Okay, one of them is, both of them have always say a specific number, right? So in this first strategy, they decide, okay, no matter what I see in Brandy's die, like I'm going to say 4 as the guess on my die. Okay, and Brandy says, okay, no matter what I see on Adriana's die, like I'm going to say 2. Okay, now when this happens, right, the event that they win is if they both if the two dice match their two outcomes. Okay, and remember that in our setup, uh, they both win or lose simultaneously. Okay, they both win if they both get their guesses right. If even one gets a guess wrong, they both lose. Okay, so in that sense, the only way that both of them can win is if the two dice indeed come up as 4 and 2. And so the event that they win is, say, set with only one possible outcome, that is 4 2. Okay, then we had this other strategy where they both say the number on the other person's die. Okay, and in this case, the event that they both win, so when will they both win? So Adriana sees Brandy's die and says the number on it. Okay, Brandy sees Adriana's die and says the number on it. Okay, and these numbers are taken to be the guess of their guesses on what their own die is showing. Okay, so in this case, they're both right if it so happens that the two throws come up as equal numbers. Okay, so if both the throws come up as 1, like they'll both be right. Both their guesses will be right, and the event that they both win is this set. Okay, 1 1 2 2 3 3, like where both the numbers are the same. Okay, and in strategy 3 was another situation where the strategy now was they guess a number, okay, such that the sum of their guess and the die that they see equals 7. Okay, and here the event that they win is the set that we actually just wrote, uh, one, this possible, this set. Okay, so now different strategies could get different, correspond to different events of them winning. Okay, and so this is where, these are examples of how you write events and so on. Okay, now finally we came, so this class, right, like we are going to assign probabilities. Okay, now uh, in our discussion last class, there were a couple of comments which I did not respond to at that point because we were not yet assigning probabilities. Okay, a lot of a lot of students were like, so many of the comments, okay, so you associate many of the comments associated the sizes of these sets with their probabilities. Okay, now this is not correct. Okay, this is one way to do things, but it's not the only way, and it's not the usual way even. Okay, there's nothing special about the sizes of the sets being related to their probabilities. Okay, here for example we could set up a probability law so that this has the highest chance of winning. Okay, we could set up a probability law where this has the highest chance of winning, and these, the second and this one and this have different probabilities of winning. Okay, now so probabilities are not, okay, so this is the first thing is about what a probability is not. Okay, probability is nothing to do with the sizes of sets. Okay, uh, we could use the sizes of sets to find a valid way to assign probabilities, but it's not the only way, and it's not even the most common way. Okay, but what is a probability assignment? A probability assignment assigns to every event some number between 0 and 1. Okay, uh, and how do you assign numbers to these events? You need to satisfy two properties. Okay, number one, the universe gets the number 1. Okay, the universe cannot be assigned anything other than 1. Okay, so that's easy. Okay, the second thing is, if you have sets that are mutually exclusive, okay, so and we'll come to this, if you have sets that are where pairwise their intersection is 0, sorry, their intersection is empty. Okay, if you have a bunch of events where pairwise the intersection is empty, okay, then the probability of their union is what you assign to their union. Okay, that number must be equal to the sum of the numbers you assign to each of the component sets. Okay, so if I assign to A and B two disjoint events, if I assign to A something like 0.2, if I assign to B something like 0.3, okay, then A union B gets 0.2 plus 0.3, which is 0.5. Okay, I don't have freedom in assigning a new number to A union B. It's already decided. Okay, does that make sense? Okay, so we'll see some examples of how we may be able to assign probabilities. Okay, and when doing this, okay, so we'll come up with something called the discrete probability law. Okay, so let's do an example. Let's do a very small example first. Okay, so let's say that the universe has 3 elements. Okay, now can you tell me all the subsets of the universe? Okay, and let's try to do it very systematically. Okay, so let's write out all the subsets. Excuse me. Let's write out all the subsets of the universe. Okay, so who wants to go first? Okay, so when we write sets, okay, so it's painful typing, I understand. So, but when we write sets, like the subsets of the universe, so when you write a subset with one element, make sure it is like this. Okay, we begin with the empty subset. Okay, this is the set with 0 elements. So very good. Then we look at subsets with just one element. Okay, then we look at subsets with two elements. To do two elements, do I skip one from this set, I skip two from this set, and I skip three from this set. Okay, and then we look at subsets with three elements, and there are no more subsets. Okay, so these are all the subsets of the universe. Okay, now let's try to come up with different probability assignments. Okay, P1 is going to be our first assignment. Okay, now a probability assignment is something like this. It associates with each of these subsets some number. Okay, and it's a number between 0 and 1. Okay, let's try something. Okay, so let's give me some mapping between these subsets of the universe to real numbers between 0 and 1. Any mapping. And I'm hoping you'll give me something that is not something that is not a probability assignment is even better, because but yeah, first give me a mapping. So anyone? So what do you want to assign to the empty set? Okay, so why 0? Everyone wants to say 0, but why? Okay, so Stephanie, so you said 0, why? Okay, so we'll see. Like, actually, you don't have a choice when you assign a, okay, so good. So if you think it can be anything, give me a number other than 0. Okay, so let's start with this. The universe gets 1. We are told to do that, so we will do that. Okay, now let's say that we give to the empty set something like 1/2. Okay, will this, so we haven't yet assigned to the other sets anything, we still don't know. Okay, but whatever be the assignment to the remaining sets, can this satisfy all the axioms that we have? Right, so Caleb, this is exactly the question we are trying to answer. Are these mappings completely arbitrary? Okay, so the mappings have to just satisfy uh, okay, so the mappings, right, so the only things the mapping has to satisfy are these three things. Like, every event should get a number between 0 and 1. You cannot say minus something. You can't say -1, or you can't say 2 for any mapping, for any event. Okay, you should assign to the universe 1, which we did. Okay, and if you have disjoint events, the probability of their union must be the sum of their probabilities. These are the three things that your mapping should satisfy, but otherwise it is completely arbitrary. Okay, but what we are trying to see is that just these three axioms actually force your probability assignments to be a certain way. Some, like for example, will this be possible, and satisfy the axioms. Right, so remember, only three axioms. The first two are like, just don't assign negative numbers and numbers greater than 1. Okay, the second one, you can second one is exactly this: the universe gets 1. Okay, the only thing you actually need to remember, okay, the only thing you actually need to remember is that disjoint unions, the probability of a disjoint union is the sum of the probabilities of the two sets. Okay, so that's actually the only thing you need to remember. The other two are kind of uh, they're not difficult to satisfy. Okay, so could we assign 1/2 to the empty set? Okay, now this is a number between 0 and 1, so we don't break that. Okay, it has nothing to do with the universe, or seemingly nothing to do with the universe. Okay, so right now let's not worry about that. Okay, so the only other axiom you worry about is what happens to disjoint unions. Okay, so could you assign 1/2 to the empty set? Okay, so you're saying it does not violate the axioms. Okay, so my claim is it actually does violate the axioms. Okay, and why is that? Right, so if I take, let us say I take this set, uh, let's say I, here we have only assigned probabilities to two sets so far. Okay, let's take the set 1 2 3, the universe set. Okay, what is this union, the empty set? 1 2 3 union the empty set. Right, it's back in the same set, because what is the union? I put in the union any element that belongs to either set. Okay, so the first set contains these three elements, so 1 2 3. This one doesn't contain anything, so it doesn't contribute anything to the union. Okay, so the union of 1 2 3 and the empty set is 1 2 3 itself. Okay, but what is the intersection between these two? Right, it's the empty set. Okay, so because the intersection is the empty set, this implies that 1 2 3 and the empty set are disjoint. Right, so they're disjoint. But what does the what do the axioms of probability tell us about disjoint sets? They tell us that the probability of 1 2 3 union the empty set, okay, must be equal to the probability of 1 2 3 plus the probability of the empty set. Right, but we know that the probability of the I mean, we know that the union of 1 2 3 and the empty set is 1 2 3 again. Okay, so what it means is that the probability of 1 2 3 must be equal to probability of 1 2 3 plus the probability of the empty set. Okay, now if I put 1/2 here, okay, there is no way this equation can be satisfied. Right, the probability of 1 2 3 cannot be both 1 and 1.5. Okay, it can only get one number and it has to get one, so that forces, actually, because this is one, this is one, it forces the probability of the empty set to be 0. Okay, does that make sense? Right, so even though we didn't say this explicitly, okay, so this is implied. Right, so your intuition was right to begin with. Right, so this can only get the number 0. This can only get the number 0. Okay, so the empty set cannot ever have a probability other than 0. Okay, okay, so let's proceed now. uh, let's proceed. Okay, so now we want to assign to the set 1 some number. Okay, anyone wants to give me a number? Okay, Samuel wants to say 1, which is fine. Okay, so 1, so the set 1 gets the number 1. Okay, now when it comes to the axioms of probability, okay, this actually fixes a number of other probabilities. Okay, can you tell me what other probabilities are automatically decided by this choice? Right? So, so twin, so what are the probabilities of 2 and 3?
They would both be 0.
Okay, and what else? So the probability of this set
Oh, yes.
has to be 0. This set has to be, you do not have a choice anymore. Okay, they have to be 0. What are the probabilities?
So then all the sets with 2 events would be 0 as well.
No, 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 no. 2 and, very good. Stephanie said 2 and 3 is 0. This has to be 0. What about 1 and 3? No, Samuel. So tell me why you say 1/2. We'll see why all of these follow. Okay, but let's first write out this one. The moment you say 1 here, actually all the other probabilities decide. So Justine, you're right. So this has to be 1. What about 1, 2? Also 1. Right? So the moment you put probability of 1 to 1, all the other probabilities get decided. Okay, why is that? Okay, so let us see. Right, so suppose we choose, okay, so suppose, so when you send by text, like sometimes I miss some of you, so but if I missed you, like just speak up, or I'll try not to, but sometimes many things scroll and I miss some of the questions. Okay, so suppose we assign the probability of this set 1 to be equal to 1. Okay, now let's see what the axioms have to say about the other probabilities. Okay, now we do know that the probability of so 1 and 2 3 are disjoint, right? So 2 3 is the complement of 1, so 1 and 2 3, they are disjoint. Okay, and their union is 1 2 and 3. Okay, so we write this axiom: the disjoint unions is sum of probabilities. Okay, and here we decided to put 1. This is our choice. Okay, this one is not our choice. The probability of 1 2 3, the universe gets the probability 1, so this is not our choice. This is kind of fixed. Okay, but this means that this also gets fixed. The probability of 2 3, the set 2 3 gets fixed to 0. Right, does that make sense? So the moment we set the probability of the set containing 1 to be 1, okay, the probability of the set containing 2 and 3 has to be equal to 0. There's no other choice there. Okay, now let's see what happens then. Like the probability of 2 3 has to be the sum of the probabilities of 2 plus the probability of. Why is this? Because the set containing just 2 and the set containing just 3, they are disjoint and their union is 2 3. Okay, now we already saw that this gets probability 0, right? So that actually fixes both these probabilities to be 0. Why? Because probabilities cannot be negative. I cannot have minus 1/2 and plus 1/2 to add up to 0. Okay, the only two non-negative numbers that add up to 0 are 0 and 0, right? So these two get fixed as well. Okay, does that make sense? Okay, so then then we have like the probability of the set 1 2. Okay, now this is the probability of the set 1 plus the probability of the set 2. Now both of this are already fixed, so this is 1 plus 0, which is 1. Okay, and same way probability of 1 3 is probability of 1 plus the probability of 3. This is 1 plus 0, which is 1. Okay, and that's how we got all these different numbers. Okay, so first, the moment you do this, actually this gets fixed. Okay, the moment this gets fixed, these two get fixed, and the moment those two get fixed, like then these two get fixed. Okay, so that's kind of the way that's kind of the way the implications go. Okay, so but the point is, like here, uh throughout, in order to, we made only one choice. Okay, we made the choice here, the probability of 1 equals 1. Okay, but the moment we made the other choice, our hands were tied, right? No other set actually we made any choice again. The probabilities of all the other sets just got fixed. Okay, so let's do another example. Same universe, but we want a different probability assignment. Okay, we still don't have a choice for the empty set. Okay, so we still don't have a choice on the empty set or the universe. They have to be 0 and 1 respectively. Okay, there's no other choice. Okay, but instead of choosing the probability of 1 equals 1, okay, choose some other number. So give me some other number. Okay, 1/4. Right, so I'm going to write as 1/4 and two other numbers. Just we are just taking the correspondence like this. Okay, so this is our first choice. Oh, Caleb, we'll come to your assignment soon. Let's do this first. I think yeah. Okay, so this is our first choice. Okay, so the probability of 1 is 1/4. Okay, now can you tell me, there is one set among these whose probability we do not have a choice. Okay, which set is that? Right. Okay, so fix probability of the set 1 to be 1/4. Okay, So this is our first choice. Okay, then we don't have a choice anymore about the probability of probability of 2 and 3. And what is this probability? What's the probability of set 2, 3? Now remember that 1 is disjoint from the set 2, 3. Very good. 1 is disjoint from the set 2, 3, and the union is the universe. Okay, and therefore the probability of 2, 3 must be 3/4. Okay, this we do not have a choice. Okay, so Donovan, I'll come to you in a second. Okay, so right now, so this we do not have a choice, so we write 3/4 for 2, 3. Okay, now what about this set? What can we tell? 2, 3 is not a question. Just no, I'm not sure I understand what that comment means. Okay, thank you. So okay, so the next thing is, what do we know about? Can we assign probabilities to the 4 remaining sets? The 4 remaining sets are just 2, just 3, 1, 3, and 1, 2. Okay, what can you tell me about the numbers you're going to assign to each of them? We still have some choices to make. Okay, unlike in the previous case, we can make a few more choices. Okay, we can actually make one choice more. Okay, but what can you tell me about, before you make any further choices, what can you tell me about the probability of this set 2? Okay, this guy. Okay, what can you tell me about the number you're going to assign to 2? You can assign 3/8. Could I assign 5/6, for example? Very good, Adriana. Why not?
Because 5/6 plus 1/4 is greater than 1.
Very good. So, and why does that what does it contradict exactly?
It contradicts the probability of the universe.
Right. So the probability of okay. So let me rephrase this. We'll come to you're right. Okay, but let me rephrase this in a slightly different way. Okay, I'm going to say that the probability of 2, just 2, has to be less than the probability of 2 and 3. Okay, why is that? Because I know that the so because I know that the probability of 2 and 3, okay, equals the probability of 2 plus the probability of 3, and all probabilities are going to be numbers that are non-negative. Okay, so if 2 and 3 gets the probability 3/4, on the right side I cannot have a number bigger than 3/4, right? Because if I assign if I assign 5/6, for example, then I'll be forced to assign a negative number for probability of 3 in order to satisfy this equality. That's not allowed. Okay, so therefore, since the probability of 2, 3 is probability of 2 plus probability of 3, but probability of 3 is greater than or equal to 0, this must be equal to the this must be greater than or equal to the probability of 2. Okay, so this means that whatever we assign to this set 2, okay, we still have a choice. Okay, but it's not any number between 0 and 1. Okay, now our choices are restricted to numbers between 0 and 3/4. Okay, that is because of our choice that probability of 1 has to be 1/4. Okay, condition on that, 2 has to get a number between 0 and 1/3. Okay, so give me a number between 0 and 3/4. I think somebody said 3/8, but give me a number easier to add, like maybe 1/2. Okay, so I'm going to take 1/2 for 2. Okay, if I set the probability of 2 to be 1/2, okay, what other sets get fixed? 1, 2. What's the probability of 1, 2? Right, so the set 1, 2 now gets fixed because we know the probability of the set 1 and the set 2, their union is 1, 2, and therefore the probability of 1, 2 is 3/4. Very good. So, okay, what other set gets fixed? The set 3, okay, the set containing just the element 3. So what is the probability? It is 1/4 again. Okay, very good. This gets fixed to be 1/4. So let me write in orange everything that gets fixed after the second choice. Okay, now what other probability gets fixed? Okay, there's only one set remaining, 1, 3. What's the probability of 1, 3? 1/2. Very good. Right, because 1, 3 is the sum of the probabilities of the set 1 and the probability of set 3. That's quarter plus quarter, which is 1/2. Okay, so does that make sense? Right, so this is a completely different probability assignment, okay, which also satisfies all the axioms. Okay, and there are like an infinity of these. Okay, because here we made two choices, right? So corresponding to every valid choice, there is there's going to be a probability assignment. Okay, in fact, like we can do this over repeatedly, but from what you see, right, like the choices we made here are for the single element sets. Okay, and when you have a discrete universe, when you have a universe like this whose elements you can enumerate like this, okay, you can enumerate the elements of the universe as 1, 2, 3, or maybe even the set of all natural numbers 1, 2, 3, 4, so on. Okay, so long as you can enumerate the elements of the universe, there is a unified way we can think about all these assignments. Okay, rather than do this complicated, okay, first choose this, first choose that, like this a little ad hoc. A more principled way is to say that sorry, I think I missed. A more principled way is to give me all these three probabilities. Okay, you need to give me three numbers in this row, okay, such that they are all non-negative and they add up to 1. Every time you give me three numbers in this row such that they're non-negative and add up to 1, okay, you can construct the probabilities of all the other elements and it will automatically satisfy all the probability laws. Okay, does that make sense? Right, so here we chose 1. The moment we chose 1, since they have to be non-negative, it meant that the other two elements here have to be 0 because these three must add up to 1. Okay, in this case we chose 1/4, but after we chose 1/4 we still had a choice on the second element because there's still some leeway for the second element. Okay, and so the choice of numbers here is 1/4, 1/2, and 1/4. Okay, now let's do a third example where this time we'll do it the more systematic way. Okay, so give me three numbers that add up to 1. Okay, so 1/3, 1/3, 1/3. Okay, now what are the probabilities? So what's the probability of 2, 3? Right, so all these 2-element sets have probabilities 2/3 each. Okay, so this will be another probability assignment. Okay, now give me a different example, something else. Probabilities of 1, 2, and 3. Right, so probabilities of 1, probability of 2, and probability of 3. Now give me 3 other numbers that add up to 1. Okay, 0, 1/2, 1/2. Right. Okay, so what's the probability of the set 2/3? One, very good. Because these two are complements, 1 and 2/3 are complements. Okay, what's the probability of the set 1/3? 1/2, very good. You can do it as either sum of these two elements or complement of the set 2. Okay, then what's the probability of 1, 2? Again, 1/2. You can again do it as complement of the set 3 or addition of these sets 1 and set 2. Okay, so right, so like we see, like there are many different ways to do valid probability assignments. Okay, when you do these probability assignments, they're not completely arbitrary. Some things are fixed. Okay, the universe is fixed, the empty set is fixed, they're both 0 and 1. Complements have to add up to 1. Okay, two sets are complements of each other, their probabilities need to add up to 1. Okay, uh, but there is sometimes some choice. Okay, and in the discrete setup, the clean way to do this is to assign probability to every one of the single element subsets. Okay, once you assign probabilities to the single element subsets such that they add up to 1, okay, everything else automatically is taken care of. Okay, and this is called the discrete probability assignment. Okay, now you see, like this particular assignment, one of the several things we came up with. Okay, in this case, okay, the probability of a set corresponds to the number of elements in the set divided by the total number of elements. Okay, but this is the only example where that is true. Right, so that's not so it's like what I'm it's like, so when you're associating the sizes of these events or sizes of the events to their probabilities, that is only true when your assignment is this very special assignment. Okay, where every single element subset has the same probability. Okay, in any other assignment it's not true. Okay, so you need to be careful. Right, so this is like a very special case. In general, the sizes of sets don't necessarily match with their probability. Okay, like for example, let's go back here. Right, for example, here is a single element subset which has probability 1. Here is a subset with 2 elements which has probability 0. Okay, so larger, so just the size of a set has usually no bearing on its probability. Okay, so you need to actually see what is inside the set. Okay, but if you are extending a set, yes, you are only increasing the probability. Okay, but generally, like two disjoint sets like this, 1 and 2, 3, right, so there's no reason their probability should be related to their size. Okay, does this make sense? Okay, so right, so next class, so this is about the axioms. So even though they're very simple to state, okay, the point is not to memorize these statements. That doesn't help. The point is to figure out how exactly these things work together. Okay, and so that's why we did like these examples. Right, Now, next class, what we are going to do is we are going to assign a probability to this universe. Okay, we are going to assign probabilities to this universe, and then we are going to talk more about like probabilities of events like this and so on. Okay. Okay. So any questions? Okay, good. So I'll stop recording.